Okay, so we shall prove the intermediate value theorem. How? Very rigorously. Okay.
Very.
Well, what does the intermediate value theorem say? Whoa, what? What does the intermediate value theorem say? It says that if f is continuous on the closed interval AB, and also let's just kind of letting f of A be less than f of B, which is just like whatever. Then the intermediate value theorem says if you give me a y value, let's call it u, between f of A and f of B, then there exists a C on that interval AB such that f of C equals u. Alright, so we all knew this, or we learned this theorem in analysis 1, and it's not too hard to believe that it is true. How are we going to prove it? Well, first,
No, I think you need a closed bracket on AB because you can have like a non-differentiable function. Oh wait, no, no, that just makes it not a function.
Good. Sorry. Good. Okay. Yeah. So here's the picture. And all right, I don't want to. It of course it asserts the existence of a single point, but it doesn't say there's only one. There could be like more, right? So I want to draw this in the most general way possible. So here is f of A, and here is f of B, and here is u. We get a little bit of A, and we get a little B in here. Oh yes. And now I want to say that it like crosses, right? But it might cross like a couple of times. What's wrong? Why is everyone laughing? Good. All right. So it might go like up and then under and like back up and something like that. Okay. And all right. I need to prove that it crosses. How am I going to do this? All right. Well, big surprise. The least upper bound axiom is going to be relevant here. That seems to be the mystery sauce which enables you to prove all of the theorems of calculus that were so obvious that there's no other way to prove it. And so here is what we're going to do. I am going to construct a set of x values and let S be the set of all x values where x is in the interval AB and f of x is less than u. And f of x is less than u. Okay, so what is S? It's a set of x values which land under u. Alright, now if your function's only going to cross this line u once, then it's like all the x values from starting with A and going up until when it crosses, right? Intuitively speaking. But if more generally, this might be like a union of a bunch of different intervals. So in this case, what is it? In this case, it's going to be like A, and all the numbers up until the first time it crosses, yeah?
Yeah.
And then when it crosses back under again, then and then it's going to be all this. All right. So this is a graphical representation of sort of this set S. It's going to be this red stuff. Okay. Note that we are going to do this proof with total and complete rigor, and so this picture is meant merely to suggest to those who still believe in intuition, like what the hell is going on. But the truth of the proof should not depend on the picture in any way. So when I eventually get to doing the proof, it's just going to go line by line, and you could just follow it with no picture at all. Okay, but that's not how humans learn, but that's how we make sure that we're right.
Oh, yes.
Oh, yeah. All right, and now what I'm going to do is I'm going to apply the least upper bound axiom to this set. So by the least upper bound axiom, I am allowed to just say that this set has a least upper bound. Oh, why? I should confirm that really quick. what does it take to show that a set that the least upper bound axiom is like applicable?
Because
It
it's
needs
a
to
bounded
be-
subset of the real numbers.
A non-empty set of real numbers which is bounded above. Okay, so S is certainly non-empty because I don't know. I guess like
just take A.
B is in it at least, or no, A is in it at least, right? Yeah. So it's so S is non-empty. That's a fact. It's also a fact that S is a subset of the real numbers, and it's also a fact that it's bounded above. Why is it bounded above?
Because all of them have to be less than B.
All of them have to be less than B, right? All the x values have to be less than B, because certainly B is not in this set, because f of B is greater than u. Okay, so B is an upper bound, and since little b is an upper bound, that means it's bounded above. So by the least upper bound axiom, I can just declare some number to be the least upper bound, and that number must exist. Okay, so let little c be the least upper bound of S. All right. And what does it mean to be the least upper bound of a set? Let's just recall. If C is the least upper bound, then sort of like two things are true, right? First of all, it's true that for all x, if x is in S, then x is less than or equal to C. Yeah. That says that C is an upper bound. And it's true that C is the least upper bound. So if C is the least upper bound, then, then it's true that for all y, if y is an upper bound, which is true if for any number in the set it's less than or equal to y, then since C is the least upper bound, C is less than or equal to y. Okay, so this is me simply outlining what it means to be a least upper bound. C is my least upper bound. By the least upper bound axiom, C exists and it's a real number. And the overall goal of this proof, can anyone just see it already? How am I going to show that there is a point where it crosses? It's like C, man. C is the number, right? So I'm gonna now, that was a weird question. I'm gonna now prove that in fact f of C is u. If I can prove that f of C is u, then I will have shown that there is a C for which the function has value u. Everyone with me? Okay. Good. All right. Well, first the understanding, then we'll get into the rigor. So I'm gonna draw some pictures. Basically, I'm going to prove that f of C is u by showing that it cannot be u. If f of C is less than u, then we have problems. And if f of C is greater than u, then we also have problems. Okay, well, what are those problems? Well, what would it mean if f of C was less than u? All right, so for this, I'm going to draw some pictures. F, B, F, A, and then U is up here, blah, 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 blah. Okay, well, what is S again? S is the set of real numbers which land under U. Well, if everything in S lands under U, if f of C is also less than U, and C is the least upper bound, what's up?
Wait, C is the least upper bound, or f of C is the least upper bound?
C is the least upper bound because the set S is the set of x values.
Oh, so C is at that dot, the second dot.
This is basically C. Yeah,
Okay.
right here. Yeah, you have to kind of keep this all straight, right?
Okay,
C
cool,
is the S is the set of x values which land under U, and in fact, if the RC by construction is going to be the last time it crosses, right? And so if this function in fact crosses multiple times, the C that we're going to prove exists is the one where it crosses last. Okay, cool?
Yeah.
Okay. All right. So if f of C were somehow to be less than U, then it would mean that that it looks something like this, right? Where this is landing underneath. And okay, the function might be but then that to me is kind of like a picture of what it would mean if f of c landed less than u. But of course, this picture is impossible because the function is continuous. Okay, so if I install like a kind of continuity patch or something now to this function, then what does that do? Well now, okay, let's try to track kind of what happens. Like, so sort of force it to be continuous or something, right? So that's f of b, that's f of a, that's u, and now instead, here was c, it's still underneath, and here was f of b, but now it's kind of like, since you forced it to be continuous, it looks kind of like that or something. But why is this impossible?
Then like C is not the least upper bound. Just find an upper bound.
Yeah, now, well, careful. I want exactly why is this a problem?
You're just an upper greater than C, better than the set S. Yeah, it's set S, so it's like what's greater. But
So therefore,
C is not an upper bound at all.
C is not an upper bound at all. Yeah, Akash's got this and maybe other people too, right? If you sort of force it to be continuous, then what you're doing is you're sort of like pulling x values which are larger than c, kind of like below the line, right? And by pulling x values a little bit bigger than c below the line, you now have some problematic x values here. Because look, there's an x value which is bigger than c, but still less than u. And that can't be. Because if x is bigger than c, but f of x is less than u, then by the definition of s, then this x value would be in s. But if x is in s, then we have a problem because c was supposed to be an upper bound, right? And since c is an upper bound, c is supposed to be bigger than everything in that set, and yet here's an x value which is in the set but bigger than c. So this is a contradiction with the fact that c is an upper bound at all. Who's with me? Since c is an upper bound, c is to be bigger than everything, but now, okay, good. All right, on the other hand, and this one's I think a little bit more subtle, and the proof's a little harder, if we consider the other possibility, okay, now here's f of a, here's f of b, here is u, Now I say, okay, well, if on the other hand we consider that f of c is bigger than u, then that means that f of c is like up here or whatever. Well, that would be the picture. But of course, that breaks continuity. And so if we kind of install continuity patch, then here's f of a, here's f of b, here's u, here's a, here's b, boom, boom, boom. Now, by forcing it to be continuous, but by keeping f of c above u, here's c. Now we have x value. Now we have x values that are a little bit less than c, but which are above the line. Okay, but if I have an x value where x is a little bit less than c, but f of x is above the line, then that means that x is what should we
not the least upper bound.
Yeah, basically, then this x is going to be an upper bound, right? But yeah, so but then x is an upper bound, and x is less than c. So this is a contradiction with the fact that c is the least upper bound. Okay. That is the gist of the proof right there. If you actually get all of that, then it means you understand it all intuitively. And if you trust pictures, then pretty much you get it. But I don't trust pictures. I only trust epsilon delta proofs because I demand rigor. So now comes the actual proof. That was all just scratch work. for like humans and stuff. Whose math is for robots. Yeah. All right.
Use the fact that f of c is greater than y.
I think I did use the fact that at some point I'm going to use that. I think so. Yeah. Oh.
Not really.
Oh, Jackson's concerned. Well, let me do the rigorous part. If you object to that, then you have to. How long do I have this period? Is it like normal time? 10:40:58. Oh, I have plenty of time. All right. Good. Good. Case one. Case one. Can you? It would be better if you move the camera to be like between Chico and Akash now, ideally. Okay. Case one is that f of c is less than u. Okay. Well, just like note that if f of c is less than u, then like u minus f of c is like a positive number. And now, what I am going to use the fact that f is continuous. So, all right, I'll put this in like a little box or whatever. Since f is continuous at x equals c, I have, thank you, Weierstrass, a formal definition of what it means for a function to be continuous at a point. And that formal definition says that for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, if I stay pretty close to c, specifically less than delta, then the difference between f of x and f of c will be less than epsilon. Yeah? Yep. Okay. Put this in a little box. This is just like background definition of what it means to be continuous. All right, and now if you sort of look at the picture, you can kind of tell exactly what to do, right? Because what does the picture say? The picture says, yo, in order to get the contradiction, I need to show that there are x values which are really, really close to c but below u. Well, if f of c is below u, then I know there must be some x values that are really, really close to c because, wait, hold on, how do I say this properly? Well, basically, I can find x values, the very definition of continuity says that I can find x values who very, very close to c, which are like arbitrarily close to f of c, essentially, right? And so what I'm going to now do is I'm going to set my epsilon to be, the gap between u and f of c, right? Because by setting my epsilon to be the gap between u and f of c, I can force the definition of continuity to give me x values which like match what my picture says. Cool? All right, good. Back up to the real proof. That was just
you got it?
all right, so we now set epsilon equal to u minus f of c, which is a positive number because, yeah. Right, and since this is true for all possible epsilon, if I challenge this definition with u minus f of c, then I receive a delta. So I'll just say, then there is a delta. Let's all agree to call it delta. Right, and what is true about this delta? Well, what's true about this delta is that for all x, if I am pretty close to c, then the gap between the function and f of c is less than epsilon, but epsilon is u minus f of c. Okay. All right, and now all I need to do is pick a number which is very, very close to c within that interval. And so a nice number to choose is like halfway between, right? So I choose, let x be c plus delta over 2. Does everyone see what I'm doing? If you look at the picture, c plus delta over 2 is that number, which is a tiny bit more than c. And so if I plug c plus delta in for x in this conditional, then of course I get that the difference between c plus delta over 2 and c, if that's less than delta, like just which it is, then f of c plus delta over 2 minus f of c is less, the absolute value of that is less than u minus f of c. It's just straight up like working the quantifiers, right? And then, of course, this is true, right? If you just do this, this just says delta over 2 is less than delta, which is true. All right, so what do I have? I currently have that the absolute value of f of c plus delta over 2 minus f of c is less than u minus f of c. Expanding the absolute value out, this says that f of c plus delta over 2 minus f of c is between u minus f of c and like f of c minus u. That's just like saying negative epsilon epsilon, right? And then I only want 1/2 of this. What's the half that I want?
Okay.
I choose to ignore now the left-hand side of the compound inequality, and I just simply get that f of c plus delta over 2 is less than u.
Okay.
All right, why is that a problem? That's exactly what I said I was going to do in the picture, right? I was going to find an x value, which is very, very close to c, but a little bit bigger, which is still less than u, right? And it's the definition of continuity that enables me to produce such a number. Well, why is that a problem?
C plus delta over 2 is now the least upper bound.
Or
It's a larger upper.
yeah, if c plus delta over 2 is less than u, then that means that c plus delta over 2 is in my set S, right?
Well,
Yeah.
then C isn't an upper bound.
Yeah.
But, of course, this is a contradiction, because c plus delta over 2 is bigger than c, so this is a contradiction with c being an upper bound, right, of S. So c was supposed to be the least upper bound of this set S, but here I found a number which is bigger than c, which is still in that set, contradicting that support. Follow?
That's not
Cool.
I just think that's not completely making sense, right? Because you have to like write it out.
Add more words in when we're up. All right, good. Case 2. This is the case which stymied me for years, but I figured it out this morning. Sort of Dilhan sort of helped, but not that much actually. Okay, case 2. So now f of c is bigger than u. And then of course that means that f of c minus u is positive. All right, so stay with me now. What am I going to do? Now I'm going to set epsilon again to be the gap, right? Because if you look over here, now I need there to be a number which is a little bit less than c, but still above u. So I'll take that gap, and coming back over here, yeah. I'll again set epsilon to be that gap. All right, so set epsilon to be now f of c minus u, which is of course positive. By the way. All right, so then there is a delta. There is a delta such that, well, just using the definition of continuity, what's true about this delta? Well, for all x, if I stay pretty close to c, specifically less than delta, then the difference between my function and f of c will be less than my epsilon, which is f of c minus u. All right, and now I think this is the most elegant way to do it, but it's a little bit long. What I now want to do is I want to consider any x value. So now just say, let x be some x value on the interval c minus delta c. All right, so I'm going to go now, I'm going to go within delta of c, but on the left-hand side only, okay?
Okay.
All right, so skipping a couple steps because, like, come on, man. This x value certainly satisfies this conditional, right? So therefore, satisfies the antecedent, right?
Just to let you know, you have 15 minutes left.
Really?
Yeah.
Good. Well, then we have more time at the end for discussion about whether we like this or not. What does the period end?
It ends at 11:08.
What time?
11:08.
11:08 for sure?
No.
No, I don't think so.
11:09? Oh, great.
11:09. Ah!
Oh, 5% slow down.
We'll finally have a logic class where we not only get to do a proof, but like discuss the consequences.
Good. Yeah. Okay. So wait, is everyone? I could write this out, but I think it's not totally necessary. If you stay with me. If you pick an x value in between c minus delta and c, then it certainly satisfies its antecedent, right? So let me just go right to the consequent. So the consequent is that this is true, right? So that the absolute value of f of x minus f of c is less than f of c minus u. Which, expanding out and getting rid of the absolute value, really says that this is between f of c minus u and u minus f of c. And now, I choose only the left-hand side of this compound inequality. So I have that u minus f of c is less than f of x minus f of c. So that tells me that f of x is bigger than u.
So why do that instead of just letting x be like c minus delta?
Because I think I need to apply this again. The time for input on this proof was before this class. I think this is a good way to do it. Just maybe no singer will make my proof shorter later. But what I really want, because I think I need it, this was kind of like a little mini sort of proof. What I think I have just shown is that for all x, so now I'm simplifying things a little bit. For all x, if x is between c minus delta and c, then f of x is bigger than u. Right? Because I took an arbitrary x on that interval, it met this antecedent, I chose only the half that I needed, so that's just like a fact. Agreed? Okay. So, since this is true, now, again, I need to pick a point which is going to be a counterexample. Don't bother changing the camera, people who are here live. I need a point which is a little bit less than c now, right? Okay, so choose, so take x equal to c minus delta over 2, for example. All right, well, if since c minus delta over 2 falls in this category, then I'll just write it out. C minus delta over 2 is certainly between c minus delta and c. And therefore, we can conclude about this that f of c minus delta over 2 is bigger than u. All right, so I have that this point f of c minus delta over 2 is bigger than u. All right, yeah. Oh, and also, here's the subtle sort of part. Also, any number between, so I'll just make another statement, which I could go into more detail, but I don't think it's necessary. If you give me any number between c minus delta over 2 and c, then that number is also bigger than u. Because that's just, I'm just kind of restricting the interval over here in this antecedent, right? Do you guys see these two sentences? This says everything between c minus delta and c lands greater than u. This just says everything between c minus delta over 2 and c lands greater than u, right? This is a smaller set of numbers, so that just follows. Okay. So now I got some important facts. Well, okay, no. Now one more sort of side thing. Side thing is, let's not forget that c is the least upper bound. So c is an upper bound. And now this is the level of rigor that no one goes into on the internet. What does it mean to be an upper bound? Well, one, by the definition of upper bound, what's true is that if x is in S, then x is less than or equal to c, right? Okay, so now take the contrapositive of that. What does that say?
If x is greater than c.
If x is greater than c, then x is not in S. All right. And by the way, over here, what does it mean to be in S again? It means that you land less than u. So if f of x is bigger than u, another way I could write this consequent is to say x is not in S. Okay, and also, it's true, of course, that C itself is not in S. Is that true? Yeah. Oh, because my assumption in this case is that f of C is bigger than U. So within this case, C is also not a member of S. All right, so the most rigorous, so let me just summarize what I have seen. What I have just seen is, or what I have just shown in little bits and pieces, I'm going to put it all right together now, that if you give me an x value between C minus delta over 2 and C, then f of x is greater than U. In other words, x is not in S. And it's true that C itself is not in S. And it's true that if x is greater than C, x is not in S. So putting that all together, I claim that if x is bigger than C minus delta over 2, then x is not in S. Contrapositive one more time, this is how my brain works. If x is in S, then x is less than or equal to C minus delta over 2. What does that say about C minus delta over 2? It's an upper bound. Yeah. So, by the definition of upper bound, if any number in that set is less than or equal to it, then C minus delta over 2 is an upper bound.
And it's less than
It's
C.
less than C.
But C minus delta over 2 is less than C, and so we have a contradiction with the fact that C is the least upper bound. By assuming that, or by letting C be the least upper bound, and assuming that f of C is greater than U, I have constructed a number which is also an upper bound, which is less than C. This is a contradiction. All right. The first case led to a contradiction with C being an upper bound. The second case led to a contradiction with C being the least upper bound. They're both contradictions, so if f of C is not less than U and f of C is not greater than U, then by like trichotomy or whatever, f of C is U, and I've shown that the function is U.
Nice.
Okay. Good. Peachy, do you like this?
I mean, it's rigorous.
Good. Ben, do you like this? Laura, do you like this?
To be honest.
It's like a real question. Yeah, you're supposed to be honest.
Intuitively, no, because it's easier to like intuitively it makes sense when you write it out. Like you can get it, but graphically it's just easier to visualize.
Yeah, wait, let's discuss. I want to have like an intense kind of philosophical conversation in the next 6 minutes or whatever about like the pros and cons of this. Give me some pros first. And Keith, put your computer away. What are some pros?